All right, so we are reading section 3.2 in this video, and we are talking about the derivative as a function. All right, so let's just take a look at the learning objectives. 3.2.1, we want to define the derivative function of a given function. Then 3.2.2, graph a derivative function from the graph of a given function. 3.2.3, state the connection between derivatives and continuity. So we want to connect derivatives with continuity, which we've talked about in the past. 3.2.4, describe three conditions for when a function does not have a derivative. So we'll look at three conditions when the derivative of a function, when a function does not have a derivative. And then finally, explain the meaning of higher order derivatives. Okay, so as we have seen, the derivative of a function at a given point gives us the rate of change or slope of the tangent line to the function at that point. If we differentiate a position function at a given time, we obtain the velocity at that time. It seems reasonable to conclude that knowing the derivative of the function at every point would produce valuable information about the behavior of the function. However, the process of finding the derivative at even a handful of values using the techniques of the preceding section would quickly become quite tedious. In this section, we define the derivative function and learn a process for finding it. Derivative functions. The derivative function gives the derivative of a function at each point in the domain of the original function for which the derivative is defined. We can formally define a derivative function as follows. And so basically what we're doing here, before we actually go into the definition, we're defining the derivative function because in section 3.1, we were finding the derivative of a function at a specific value. So we wanted to find, f prime of 2 for this given function f. And that gave us the tangent line to the function at x equals 2. I was trying to see if they had a graph of the function. They don't. And it takes, a good amount of work to find the derivative at that x value. So what if I also ask, okay, well, for the same function f, find f prime of 4. Well, now you have to do essentially this work again, and then f prime of 8 or f prime of 1.5, right? For each one of these problems, there's going to be, work. A lot of work that we have to do to find each of these values. We could find them all using the limit definition, but notice, f prime of 3 is one we haven't mentioned. The rate of change, the derivative at an x value of 3. Well, this can get really long really fast. And so in section 3.2, we start talking about the derivative instead of at a point, we talk about it as a function. So let's take a look at the definition. Let f be a function. The derivative function, denoted by f prime, is the function whose domain consists of those values of x such that the following limit exists. And notice that the limit is just the limit definition that we saw before. So f prime of a, before in section 3.1, this was the limit as h approached 0 of f of a plus h minus f of a divided by h. So now instead of plugging in a specific value a, we're just going to leave this as the variable x. Okay. Now a function f of x is said to be differentiable at a if f prime of a exists. More generally, a function is said to be differentiable on S if it is differentiable at every point in an open set S. And a differentiable function is one in which f prime of x exists on its domain. Okay, so just a couple more definitions. Now, yeah, so we can use this function here. Oops, let me use, this is a function in terms of x, and then we can plug in values. Once we've simplified this limit here, then we can plug in specific values of a, but we only have to do the limit once, and then we can plug in our values, as we'll see in the next few examples. So finding the derivative of a square root function. We want to find the derivative of f of x equals the square root of x. And so it says start directly with the definition of the derivative function and use equation 3.1. Okay, so let's take a look. Well, yeah, and actually we can do it. We can do it together here. So the derivative function f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. And so f of x is the square root of x. F of x plus h is equal to the square root of x plus h. And so this is equal to the limit as h approaches 0 of f of x plus h, which we said is the square root of x plus h, minus f of x over h. And then we, here we have our radicals. We saw in a previous section that we can simplify this algebraically by multiplying by the conjugate on both the top and the bottom. If you tried direct substitution, you would get an indeterminate form of 0 over 0. You can mentally plug in h equals 0, and you'll see that that happens. So we need to algebraically reduce this somehow. So we'll multiply here the square root of x plus h times the square root of x plus h, just x plus h, or the square root of x plus h squared if you want. The square and the square root cancel. Then when we multiply these middle terms here, multiplying by the conjugate, those two middle terms are going to cancel, so I won't write them out. And then the next term is going to be the opposite of the square root of x times the square root of x, which is just going to be x. We divide this by h times the square root of x plus h plus the square root of x. You can see that the x's cancel in the numerator, positive x and negative x. And then it turns out that we're going to have just an h on top, and that's going to cancel with the h on the bottom. And so this gives us the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. Now we can do the limit as h approaches 0. We can do direct substitution. This is the square root of x plus 0 plus the square root of x. And this is equal to 1 over the square root of x plus the square root of x, which is equal to 1 over twice the square root of x, which can be written. Yeah, I mean, this is the derivative function here, f prime of x. And so if we wanted to rewrite this, keep in mind that this is 1 over 2 times x to the 1/2. And so we could also write this as 1/2 times x to the negative 1/2. All right, and there's our derivative function. Exactly what they got. Okay, finding the derivative of a quadratic function. Well, how would we do this? Same limit. We can use the same limit if we want to. So f of, let's see, the limit as h approaches 0 of f of x plus h minus f of x divided by h. I'm not sure if I'll have enough room in this margin here, but we'll give it a shot. F of x plus h is going to be x plus h squared minus 2 times x plus h. And this isn't going to simplify too much, but we can try to FOIL this here and see what we get. So this is x squared plus 2xh plus h squared minus 2x minus 2h. We don't really simplify much there, but we can plug in now. The limit as h approaches 0 of f of x plus h, x squared plus 2x h plus h squared minus 2x minus 2h. That's f of x plus h minus f of x. F of x is x squared minus 2x. Make sure to put the parentheses there so you can make sure to distribute this negative sign in the numerator, which I'll show next. We distribute this negative sign. This is a common thing that gets forgotten. And so this is the limit as h approaches 0 of, and we can see that it turns out that the x squareds are going to cancel because we have an x squared here and a minus x squared after we distribute the negative. And then we also have a negative 2x. And then when we distribute the negative, this is going to be a positive 2x. So those are going to cancel. And so we're going to get 2xh plus h squared minus 2h over h. And notice if you do direct substitution here, you're going to get 0 over 0, an indeterminate form. So we can't do direct substitution just yet. We want to cancel out this h at some point. And we did that earlier in this step here where we got rid of the h's. Well, we want to do that here as well. And so we're going to factor an h from the numerator, 2x minus h minus 2 divided by h. And so here we have those h's that can cancel. That's going to get rid of our 0 over 0 problem. And we're going to be able to use direct substitution now. So this is equal to 2x minus h is approaching 0. So we'll use direct substitution and we get 2x minus 2. So f prime of x is equal to 2x minus 2. All right, and the exact same steps they do here in that book. All right, so let's continue. We use a variety of different notations to express the derivative of a function. In example 3.12, we showed that if f of x equals x squared minus 2x, then f prime of x equals 2x minus 2. If we had expressed this function in the form y equals x squared minus 2x, we could have expressed the derivative as y prime. So instead of f of x and f prime of x, we use y and y prime of x. Or we could even write it as dy dx, because essentially we are taking the derivative. So if we have y equals x squared minus 2x, we are taking the derivative and the derivative we're taking is with respect to x. So this is our notation for it. And that can be written as just dy dx. This represents the derivative, which if we differentiate the right side, we ended up getting 2x minus 2. So dy dx is another notation for the derivative function. We could have conveyed the same information by writing d dx of x squared minus 2x. That's exactly what I just wrote there in purple. Thus, for the function y equals f of x, each of the following notations represents the derivative of f of x. So we mentioned f prime, dy dx. You can use y prime or d dx of the function f of x. The more common ones are probably f prime, dy dx, and then y prime. In place of f prime of a, so suppose we're wanting to calculate the derivative out of a certain value a, we could also use the notation dy dx and then this vertical bar, which means it's evaluated at x equals a. Use of the notation dy dx, called Leibniz notation, is quite common in engineering and physics. To understand this notation better, recall that the derivative of a function at a point is the limit of the slopes of the secant lines as the secant lines approach the tangent line. The slopes of the secant lines are often expressed in the form delta y over delta x, where delta y is the difference in y values corresponding to the difference in the x values, which are expressed as delta x. Thus, the derivative, which can be thought of as the instantaneous rate of change of y with respect to x, is expressed as dy dx is equal to the limit as delta x approaches 0 of delta y over delta x. Okay, so just notation there. All right, so graphing a derivative. How do we graph a derivative? We have already discussed how to graph a function. So given the equation of a function or the equation of a derivative function, we should be able to graph it. Given both, we would expect to see a correspondence between the graphs of these two functions, since f prime of x gives the rate of change of a function f of x, or the slope of the tangent line to f of x. So yeah, I mean, they're related somehow, right? F of x and f prime of x. F prime of x is giving you the rates of change of the function f of x. So if you look at both of their graphs, they should be related in some way. We'll continue reading. In example 3.11, we found that for f of x equals the square root of x, f prime of x equals 1 over 2 times the square root of x. This should have parentheses or if we graph these two functions on the same axes as in figure 3.12, we can use the graphs to understand the relationship between these two functions. First, we notice that f of x, so f of x is in blue down below, f of x is increasing over its entire domain. Since f of x is increasing over the entire domain, this means that the slopes of the tangent lines at all points are positive. Consequently, we expect that f prime of x is greater than 0 for all values of x in its domain. So, you know, if I were to check, let's say, let's just choose a random value here. Actually, let's check, say at x equals 1. Right, x equals 1, we see that the tangent line or the rate of change of the function, since it's an increasing function, the rate of change should be positive. So the slope of the tangent line should be positive. The derivative function f prime of x gives you the rate of change of f at that x value, x equals 1. So since the rate of change is positive, because f is increasing, then the value of the derivative function should be positive. And you can see that at 1, the derivative function does have a positive value. It looks like it has a positive value of 1/2. And then what's another thing that we can note here? Let's choose a different point. I'll choose this one here, which is roughly at like 1/4 for the x value of 1/4. What do you see here? The slope of the tangent line seems steeper. Since the slope of the tangent line is steeper, that means that the rate of change is greater. Right? This function is increasing faster in the beginning. And so what that means is that the derivative function should have a larger value for this x value. And we see that that's true. The derivative function has roughly a value of 1 there, which is a larger value than it has at x equals 1. Okay, so hopefully you see that relationship. Furthermore, okay, so we'll continue reading. And I think they just say this in the paragraph here. So it says, furthermore, as x increases, the slopes of the tangent lines to f of x are decreasing. And we expect to see a corresponding decrease in f prime of x. We also observe that f of 0 is undefined. And that should be f prime of 0, actually. I believe this is a typo because f of 0 is defined. F of 0 is the square root of 0, which is equal to 0. That is defined. But f prime of 0, that is not defined. F prime of 0 is equal to 1 over 2 times the square root of 0. And you can see that this is undefined, right? We have 1 over 0. So f prime of 0 is undefined. That means that the rate of change at x equals 0 is undefined. So, and that the limit, let's look at this limit here. What is the limit as x approaches 0 from the positive side of the derivative function f prime of x? We see that that limit is positive infinity. F prime of x shoots up to infinity. And that corresponds to a vertical tangent to f of x at 0. So you can see that, let me delete the lines that I've done so far. Yeah, at 0, what is the tangent line looking like? And it looks like it's going to be a vertical tangent line there. And since what's the slope of vertical line? We've talked about that. I mean, that's been talked about in previous classes like algebra. A vertical line, we say the slope is undefined. And that's why the function f prime, which gives you the slopes of the tangent lines, is undefined at x equals 0. Okay, so it's matching up to what we know from before. In example 3.12, we found that for f of x equals x squared minus 2x, the derivative function f prime of x equals 2x minus 2. The graphs of these functions are shown in figure 3.13. Observe that f of x is decreasing for x is less than 1. So you can see that, yeah, when x is less than 1, this function is decreasing. So if this function is decreasing, what kinds of slopes would it have for tangent lines, right? The tangent lines would have slopes that are negative. And so that's exactly why the function, the derivative function, has negative values. Because these negative values are saying for this x value, the original function f has a negative sloping tangent line. For these same values of x, f prime of x is less than 0. Okay, continuing on here. For values of x larger than 1, so that would be, over here on this side of the parabola, f of x, the parabola, is increasing. And notice that, right, this increasing starts, the function starts increasing after x equals 1. And take a look at the derivative function, which gives the slopes of the tangent lines. It is positive. It has positive values when x is larger than 1. And then finally, the last thing to note here is that also f of x has a horizontal tangent line at x equals 1. Yeah, you can see the horizontal tangent line there at x equals 1. And so what is the slope of that tangent line? If it's horizontal, the slope is 0. So the derivative function has a value of 0 when x is equal to 1. Okay. All right. So let's go ahead and it says, use the following graph of f of x to sketch a graph of f prime of x. And so we'll sketch it on here. I believe the solution is right before. So we should look at the intervals of increasing and intervals of decreasing. So where is this function increasing? And I should have done this in a different color. So I'll start with the increasing and I'll do it in blue. This function is increasing, right, on this interval here. From blue dot to blue dot. And that looks to be from -2. Let me use -2 to 3. Is it increasing anywhere else? No, I'm going to show decreasing with red. I'll just highlight it in red or color it in. Intervals of decreasing are from -4, it looks like, to -2. Also, another place where it's decreasing is over here from +3, it looks like, all the way to +7. So from 3 to 7. And then we have, horizontal tangent lines at -2, x equals -2, and at x equals 3. Okay, so wherever the function is decreasing, or let's start with the tangent lines actually. Whenever we have horizontal tangent lines, that is where our derivative function is going to have a value of 0 because the slope of that tangent line is 0. So I'll mark those. Okay, so we have 2 points there. And now, wherever our function is decreasing, which is on the interval from -4 to -2, our function, our derivative function will have values that are negative. There we go. Wherever our function is increasing, our derivative function will have positive values. And then wherever our function is decreasing again, our derivative function should have negative values. So we have this roughly as our sketch here. And you could say, well, wait a minute, why did you turn this function around, right? I mean, well, for one reason is we drew those 2 purple points and we know that the function has to go, from one of those points to the other eventually. But if you look at the slopes of the tangent lines on the interval from -2 to +3, let's take 3 points, for example, here. We'll take, actually, let me move back a little bit. This point here, and I will use a different color. Let's use green. How is the slope of this tangent line compared to the slope of the tangent line somewhere in here? And then comparing it to a slope of a tangent line over here. Right, we had drawn purple tangent lines when x was equal to -2 and it was horizontal, and when x was equal to 3 and that was horizontal. So it's hard to describe here, but hopefully you can see that when we start at the lower purple line, and as we start to move our x values, as the x values start to increase, our tangent line gets steeper from the purple lower purple line to the first green line. Yeah, here we go. Oops. From this purple line, we have slope of 0, so we have a value of 0. And then we start to increase the slope of our tangent line. So the value of our derivative function will increase. And then finally, it increases, it increases further in here. So this function should increase even more. But then eventually the tangent line slopes start to decrease. Notice the slope here is smaller now. And so this function should start to decrease and then finally reach a slope of 0 or a derivative value of 0. And then since the function starts to decrease, the tangent lines would now be negative, which means that we would have negative function values for the derivative function. Okay, let's take a look at the sketch that they have here. Yeah, and then of course, it's a sketch, so it's not going to come out perfect, but it gives us a rough idea of what the derivative function looks like. So let's take a look at, let's read the solution. It says the solution is shown in the following graph. Observe that f of x is increasing and f prime of x is larger than 0 on the interval from -2 to +3. Yes, that's what we said. Also, f of x is decreasing and f prime of x is less than 0 on the interval from -∞ to -2. Okay, yeah, we only went as far as -4. I mean, the picture in the book does as well, but they say from -∞, sure. And on the interval from 3 to +∞, and we went from 3 to 7. Yeah. Also note that f of x has horizontal tangents at -2 and at 3. Yes. So the derivative function's value at -2 and 3 should be 0 at both of these locations. And that's exactly what we showed here with those purple dots. Okay, cool. So what about derivatives and continuity? What do these two have to do with each other? So let's read. Now that we can graph a derivative, let's examine the behavior of the graphs. First, we consider the relationship between differentiability and continuity. We will see that if a function is differentiable at a point, it must be continuous there. So that's an important statement there. If a function is differentiable at a point, then it must be continuous there. However, a function that is continuous at a point need not be differentiable at that point. In fact, a function may be continuous at a point and fail to be differentiable at the point for one of several reasons. And we'll take a look at an example of that coming up soon. So here's theorem 3.1, differentiability implies continuity. And here's the theorem. Let f of x be a function and a be in its domain. If f of x is differentiable at a, then f is continuous at a. Okay, so yeah, pretty simple statement here, but it says if a function f is differentiable, if its derivative exists at a, then f should be continuous there, or it is continuous there, according to this theorem. And there's a proof. This is kind of a nice proof, so I do want to go over it. We can write it on the side here. I'll just rewrite it, even though they have it done here. And basically, we say, so if, right, this is the statement that we're saying, if f of x is differentiable at a, so this is the assumption. And under this assumption, if this is true, then we should be able to show that f is continuous at a. So we can assume f prime of a exists. Okay. If f prime of a exists, then f prime of a is equal to the limit. Right? How did we define this? And there were two different ways that we defined f prime of a. In this proof, we'll use the limit as x approaches a of f of x minus f of a divided by x minus a. Okay, so if the derivative exists at x equals a, then this limit must exist. And so now we want to somehow show that f is continuous at a. Remember that continuity, basically we had to show that for continuity, we needed to show, and I'll write it down here, that the limit as x approaches a of f of x was equal to f of a. This is from section 2.4. Okay, so how can we do this? Well, there's a nice little trick, actually, that we'll use. And first, let's start with looking at the limit as x approaches a of f of x. Well, what can we do with this limit here? We can actually, to this f of x, we can add and subtract f of a. Now, this is just for the proof here. You know, you could say, well, yeah, sure. I mean, I can add something and take it away at the same time. That's not really changing the limit. We're not changing the value there. And then next, we can multiply, right? So we have this new limit. We can take this part here, multiply by x minus a, and at the same time divide by x minus a. Again, we're not really changing the value here because we're technically multiplying by 1, essentially. And according to some of the limit theorems that we saw in section 2.3, we can break this limit up and rewrite this as the limit as x approaches a of f of x minus f of a divided by x minus a times the limit as x approaches a of the other factor, x minus a, plus the limit as x approaches a of the final term here, it was f of a. Put parentheses here just to split up these limits. Okay, Well, what is this first limit here? This is exactly the what's written in green up above. This is f prime of a. What is the limit as x approaches a of x minus a? We can do direct substitution. Substitute in a for x, and you get the limit of a minus a, which is 0. The limit as x approaches a of x minus a is 0, plus the limit as x approaches a of a constant f of a, that would just be f of a. And so notice that this 0 times f prime of a goes away, and what we're left with here is f of a. Keep in mind that we started with the limit as x approaches a of f of x. And so this gigantic, or I mean, somewhat big string of equalities says is that the limit as x approaches a of f of x is equal to f of a. And this shows that the function f of x is continuous under just using this assumption here that the function was differentiable at a. So if the function is differentiable at a, we can show that it's continuous at a. So we conclude that f is continuous at a. All right, that's a very nice proof. Let's continue reading. So if a function is differentiable, then it is continuous wherever it's differentiable. We have just proven that differentiability implies continuity. But now we consider whether continuity implies differentiability. To determine an answer to this question, we examine the function f of x equals the absolute value of x. This function is continuous, and you know what this looks like. There isn't a graph right here. They might have it on the next page, but let's just quickly sketch it. Right, the function y equals the absolute value of x. You've seen this one before, probably, and it looks something like this. Something like that. This function is continuous everywhere. You can see it's continuous. However, f prime of 0 is undefined. This observation leads us to believe that continuity does not imply differentiability. And let's explore further. For f of x equals the absolute value of x, f prime of 0, what is f prime of 0? We'll use the limit as x approaches 0 of f of x minus f of 0 over x minus 0. F of x is the absolute value of x. F of 0 is 0, x minus 0. So we have the absolute value of x over x. And my notation is sloppy here. I should have put a limit. That is, I should put that limit here. The limit as x approaches 0, the limit as x approaches 0. And so this limit here, what is this limit equal to? Well, if we do direct substitution, it looks like you get 0 over 0 in indeterminate form. But we can actually break this down to the single-sided limits. So let's take a look at the left-hand side, the limit as x approaches 0 from the left of this absolute value of x over x. And remember that this is going to be essentially the, so for values of x that are to the left of 0 but approaching 0, you can see that you can plug in any value like negative 0.01. And when you take the absolute value of negative 0.01 and divide it by negative 0.01, you see you're going to get negative 1. And you can choose a smaller value, negative 0.0001, divided by negative 0.0001. Again, we get negative 1. The value that we are approaching from the left side is negative 1. then if you look at the limit from the right-hand side, the limit from the right-hand side is going to be +1. And so since the limit from the left and the limit from the right do not agree, then the limit, the double-sided limit here, does not exist. And therefore, f prime of 0, the derivative of this function at x equals 0 does not exist, even though this function is continuous at x equals 0. So we have just shown that continuity does not imply, so we'll put imply and cross it out, does not imply differentiability. But differentiability does imply, I'll put implies continuity. Okay. So we just showed a counter example to this. We showed a continuous function, the absolute value of x, that is continuous at x equals 0, but is not differentiable at x equals 0. But theorem 3.1, it was, we proved that this statement is true, that differentiability implies continuity. Okay, so let's consider some additional situations in which a continuous function fails to be differentiable. Consider the function f of x equals the cube root of x. We can look at the derivative function at 0, f prime of 0, similar to what we did with the absolute value of x. If you write this out here, they kind of skipped a couple of steps, or yeah, so let's go ahead and write it out. F prime of 0 is equal to the limit as x approaches 0 of f of x minus f of 0 over x minus 0. So the limit as x approaches 0 of f of x, this is the cube root of x, minus the cube root of 0 over x minus 0. So how can we write this? The cube root of x can be written as x to the 1/3. 0, of course, you know, both of those zeros can kind of just get canceled because, and this is x to the 1 in the denominator, which we can write x as x to the 3/3. And so using our rules of exponents, this is the limit as x approaches 0 of x to the negative 2/3, or as they've written it here in the book, we can write it as 1 over x to the 2/3, or finally the limit as x approaches 0 of 1 over the cube root of x squared. Now the limit as x approaches 0 is going to be positive infinity. And what does that mean? So the derivative function looks like it has a value of 0 here, but the limit is when x is equal to 0, the limit is infinity. So f prime of 0, we say, does not exist because f prime of 0 is defined in terms of a limit. The limit only exists if it is equal to a finite real value, and infinity is not a finite real value. So what does this mean in terms of the graph? Remember that the derivative is giving us the slope of the tangent line. And so here, the tangent line would have a slope. Essentially, you could kind of say that it's infinitely large. It is actually undefined. The slope of this vertical line is undefined. So a quick look at the graph of f of x clarifies the situation. The function has a vertical tangent line at 0. And so the slope of a vertical line was never defined in a previous class. It was always determined to be undefined. All right, so that's another case. If you have a vertical tangent line or like some corner like this in the absolute value of x, then the function will not be differentiable. The derivative will not exist at those values where those kinds of things occur on a graph. Next, the function f of x equals x sine of 1 over x if x is non-zero, and 0 if x is equal to 0, also has a derivative that exhibits interesting behavior at 0. And then we see that f prime of 0 is equal to, the limit as x approaches 0 of the function f of x minus f of 0 over x minus 0. This is just the limit as x approaches 0 of sine of 1 over x. And this has come up in our videos before in a different section. This limit does not exist, essentially because the slopes of the secant lines continuously change direction as they approach 0. So yeah, you can see, if you can see that this function is oscillating back and forth. And if you look at the tangent line that went for a single x value, the tangent line is negative. But then as you get closer to x equals 0, well, now the tangent line, has a positive slope. And then, you get closer and closer and you see it's going to oscillate back and forth. And this limit is not approaching a single value. It oscillates back and forth between positive and negative values. So this limit does not exist. Therefore, we say that the derivative is, or that this function is not differentiable at x equals 0. So in summary, we observe that if a function is not continuous, it cannot be differentiable, since every differentiable function must be continuous. However, if a function is continuous, it may still be failed to be differentiable, as we just saw in the few examples. We saw that f of x equals the absolute value of x failed to be differentiable at 0 because the limit of the slopes of the tangent lines on the left and right were not the same. Visually, this resulted in a sharp corner. So that's what we want to kind of take away in terms of the visual. It was a sharp corner on the graph of the function at 0. From this, we conclude that in order to be differentiable at a point, the function must be smooth at that point, not like some sort of sharp corner. As we saw in the example of f of x equals the cube root of x, a function fails to be differentiable at a point where there is a vertical tangent line. So it fails to be differentiable at a point where there is a vertical tangent line. As we saw with f of x equals x sine of 1 over x, a function may fail to be differentiable at a point in more complicated ways as well. Okay. And so finally let's take a look here. Yep. We have one example, 2 examples left before we finish the section. So let's go ahead and finish. A piecewise function that is continuous and differentiable. So there's a toy company that wants to design a track for a toy car that starts out along a parabolic curve, then converts to a straight line. The function that describes the track is to have the form f of x equals, and notice that we have a parabolic part here when x is less than -10. And then the function that this track is going to follow becomes a linear function when x is larger than or equal to -10, where x and f of x are in inches. For the car to move smoothly along the track, the function f of x must be both continuous and differentiable at -10. We want to find values of b and c that make f of x both continuous and differentiable. Okay, and of course it makes sense that this track here at the red dot is where we're worried here. This track should be definitely continuous, because if there's a jump discontinuity, an infinite discontinuity, or a removable discontinuity, especially with a jump discontinuity, you can tell you know, if the track was down here somewhere, well, yeah, that car would not run smoothly across that. And so we want it to be continuous, but then we also have, you know, we want it to be differentiable as well. We don't want there to be like a corner or something, so that the car can travel smoothly. So let's go ahead and take a look. For the function to be continuous at x equals -10, yes, what does it mean for it to be continuous at x equals -10? The limit as x approaches -10 of our function f of x should be equal to f of -10. Now, let's take a look here. So we can break up this limit into two parts. Remember that for every two-sided limit, you can break it up into the single-sided limits. So the limit as x approaches -10 from the left of our function, well, on the left-hand side, it's defined using this definition here. And let me see if I can take our function definition here. So the limit as x approaches -10 from the left of this function, what we're going to do is basically just use that rule 1/10, and we're going to use direct substitution. This is instead of x squared, we have -10 squared plus b times -10 plus c. Okay, so we use direct substitution. Now, what is f of -10? When x is actually equal to 10, to -10, we are using the second rule. So we can find f of -10 by plugging in. So we have -1/4 times -10 plus 5/2. And this is going to be, what is this here? Negatives cancel, and we get 5/2 plus 5/2, which is 5. So notice earlier that we said that the limit needs to be equal to f of -10. Well, the limit from the left-hand side, we just wrote down here. And so this needs to be equal to f of -10, which is 5. We can simplify this a little bit. -10 squared is 100, divided by 10 is 10, minus 10b plus c equals 5. And so this is going to give us an equation here. If we subtract 10 on both sides, this is going to give us the equation. And why not? Let's go ahead and actually add 10b to both sides as well to isolate the c to solve for one of these unknowns. And so we get c on the left-hand side is equal to, let's do 10b minus 5. Okay, so we have an expression for c. Now, let's continue reading here. It says, for the function to be differentiable at -10, we also have to have f prime of 10, which is defined in terms of this limit. This limit must exist. It says, since f of x is defined using different rules on the right and the left, we must evaluate this limit from the right and the left and then set them equal to each other. Okay, so this limit here from the left-hand side is going to be, let's f of x minus f of -10, and then x minus a negative, that's positive 10, right? Minus a negative gives us our positive. And so this f of x here is going to be, we're going to use, since we're approaching from the left-hand side, we're going to use that first rule from before. And we can simplify this. Now, what are we doing here? In place of c here, we're going to substitute what we know c is equal to, 10b minus 5, and you see that that's done in this next step. Now we try to simplify. Let's go ahead and take a look at what got simplified. At the same time here, they multiplied by 10 on both the top and the bottom to try to get rid of any fractions, mostly this 1/10 here. And so if we multiply everything by 10, notice we have x squared minus 100. The minus 100 comes from this negative 10 here, multiplied by that 10 on the outside, plus 10bx plus 100b over 10 times x plus 10. We can factor the numerator. The numerator factors to x plus 10 times x minus 10 plus 10b. You can check that using multiplication. Then the x plus 10s cancel. And then we can do, once those x plus 10s cancel, we should be able to plug in a negative 10 because it won't make either of those factors equal to 0. And so if we use direct substitution from there on, if we plug in negative 10, we get, what do we get here? We get negative 10. I'll plug it in place of x. So we have a negative 20 here, plus 10b. When we divide by 10, our negative 20 becomes negative 2. And then our plus 10b divided by 10 is going to become just a positive b. So the limit from the left-hand side is b minus 2. The limit from the right-hand side hopefully won't be as challenging, because the limit from the right-hand side is going to use the rule from the right-hand side, which is a linear function. And so from the right-hand side, we have f of x, which is our function, f of x, minus f of negative 10. F of negative 10 is still negative 5. And then on the bottom, x minus negative 10 is x plus 10. We can simplify this by multiplying. It looks like they multiplied by the least common denominator. Let's try doing that. The least common denominator here is, or did they do that? Yeah, let's just try multiplying by 8, and we'll do it that way. So we multiply by 8. Negative 1/4 x times 8 is negative 2x. 8 times 5 is 40, divided by 2 is 20, so that's plus 20, minus 8 times 5, which is 40, divided by, and let's leave this here just as 8 times x plus 10. Let's see what happens. Negative 2x minus 20 is what we end up with on top. 8 times x plus 10, and you can see that we can cancel a 2. If we factor from the top, we can factor a 2, and actually a negative 2, it looks like. Negative 2 factors and leaves us with x plus 10. On the bottom, we have 8 times x plus 10. And if we cancel a factor of 2, we're left with just a negative 1 on the outside, and then a 4 on the bottom, and 2 factors of x plus 10, which is where they go from here. We can see that we can cancel these x plus 10s. And so that leaves us with a negative 1/4. The limit is negative 1/4. Now, don't forget that the limit from the right-hand side and the limit from the left-hand side, they need to be equal to each other in order for this limit, this double-sided limit to exist, which has to exist because we were told that the function needs to be differentiable. So b minus 2 is equal to 1/4, and that's what's given here. We can solve for b there. B is equal to 7/4, and now we can finally plug in our value of b into our formula here for c in terms of b, and we get a value of c of 25/2. Okay, so we have those two values. We can graph it, and they already gave us the graph here. The function will be both continuous and differentiable for those values of b and c. 7/4 for b and 25/2 for c. All right. So higher order derivatives, the last part it looks like. And so can we take more derivatives, right? Higher order derivatives. What does that mean? In this section, we'll just briefly cover this, and we'll talk about higher order derivatives later in this class. But the derivative of a function is itself a function, right? So the derivative of a function is itself a function. So we can find the derivative of a derivative, because if the derivative is a function and we know how to differentiate functions, why can't we differentiate the derivative? Yeah, we can. For example, the derivative of a position function. So the derivative, we're going to talk about this more later, but the derivative of a position function is the rate of change of position. That is known as velocity. Then the derivative of velocity is the rate of change of velocity, which is called acceleration. The new function obtained by differentiating the derivative is called the second derivative. Furthermore, we can continue to take derivatives to obtain the third derivative, fourth derivative, and so on. Collectively, these are referred to as higher order derivatives. The notation for the higher order derivatives of y equals f of x can be expressed in any of the following forms. And so if you like the f prime notation, so for f of x, right, the first derivative was f prime of x. So the second derivative can be written as f double prime of x, and so on. When you get to the fourth derivative, right, so you don't have to write f prime 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 like quadruple prime of x. You can write just, how many times you've taken the derivative instead. That way, if you go to like the 100th derivative or something like that, that would look kind of ridiculous with 100 apostrophes. So you could just write 100 in parentheses. Similarly, if you like the y and then you differentiate, you get y prime, differentiate again, y double prime, and so on. If you like the dy dx notation, dy dx, if we take the derivative with respect to x again of dy dx, this ends up being written as d squared y dx squared, right? So that would be the notation for the second derivative, third derivative, fourth derivative, and so on. And then it is interesting to note that the notation for d squared y dx squared may be viewed as an attempt to express the derivative of the derivative more compactly. Analogously, the third derivative, is basically you're taking the derivative of the derivative of the derivative of y with respect to x. Okay, so how do we find, in this last example here, how do we find the second derivative? Well, we're just going to find the derivative twice. So I won't write out all the work for this one because we did one similar to this in a few minutes ago. And so let's just take a look at the derivative. So for the function f of x, it's a quadratic function. We want to find f prime of x. So we can do that using our definition of the derivative function, which is defined in terms of the limit, right? So it's basically just the limit as h approaches 0 of f of x plus h minus f of x divided by h, right? And so f of x plus h is done here, minus f of x over h. We can try to simplify this. Now, it's going to take a lot of algebra distribution. And so it simplifies to this line here. We want to get rid of an h. Notice that all of these terms here have a factor of h, and h. So there's going to be an h that cancels if you were to factor an h from the numerator. And then you can use direct substitution on h as h approaches 0 once you've simplified. And as h approaches 0, we get the derivative is 4x minus 3. And then to find a second derivative, you just take this function, f prime of x, and it's written right underneath, is 4x minus 3. This is our new function. And we take the derivative of it. And so we use the same limit definition for the derivative. And this one's a lot easier because the linear function is a simpler function. We have our limit definition right here for 4x minus 3. We simplify this using the distributive property, factor out an h if we need to, and cancel out h's. And we end up getting that the limit as h approaches 0 of 4, we've seen this before, is 4. And so our second derivative of the function f double prime of x is equal to 4. All right, so that's kind of nice. We start with a somewhat complicated quadratic function. Then we have a linear function. And then we have another linear function, but it's actually constant, just 4. Okay. Oh, maybe that wasn't the last example. There's one more. So briefly talking about this one here. How do we find acceleration? Well, in example 316, the position of a particle along a coordinate axis at time t in seconds is given by s of t in meters. Find the function that describes the acceleration at time t. And so the acceleration, as was mentioned in one of the paragraphs a few moments ago, is the second derivative of the position function. So if you were to take your function s of t, and this is a position function, then s prime of t, this is the rate of change of position, this is known as the velocity. And then if we find out how fast the velocity is changing, the rate of change of the first derivative is the second derivative, and this is called the acceleration. So it's just going to be basically the same example as before, but finding the derivative twice, except now we're putting it in a context of position, velocity, and acceleration. Oh, and that's exactly what it says here. V of t, we'll use v to describe velocity, is just the first derivative of the position function. And then the acceleration function is the first derivative of the velocity function, which is the second derivative of the position function, however you want to write that. And so here it says we begin by finding the derivative of s of t, and we're going to use the limit definition again. Again, since it's a quadratic function, it's just going to take a little bit of algebra. We simplify the limit, and we get that the derivative s prime of t is equal to 6t minus 4. Okay, so this is our, you could actually even call it v of t if you want to. This is our velocity function. Now, how do we find the acceleration function? We take the derivative of the velocity function. So, or the second derivative of the position function, same thing. And so this is, again, the second derivative. We use, notice how we are now using the limit definition on s prime, because we're taking the second derivative, we're applying the rule for the derivative function to the first derivative already. And so we have our limit for the function 6t minus 4. We simplify that, cancel out any h if we need to, and we get 6. So our acceleration function, a of t, and it turns out that this actually does not depend on t. It ends up coming out to a constant, and the units for this is meters per second squared. And the units for the velocity function were in meters per second. Because, of course, the position function is in meters, and the time was in seconds. So, all right, that is it. Problem 310 here. For s of t equals t cubed, finding a of t. That is not too difficult to do for this function here. It's a cubic function, but well, it's not too bad. It actually does take some algebra there. but you can give it a try. All right, that was section 3.2, and we will stop there.